Okay, hello. Welcome back to AMT 151 Basic Electricity. I'm just a couple minutes early, but I'm going to go ahead and get started. First, I want to tell you guys that you need to check Canvas because we're going to be having an exam next week on batteries. So I put an announcement up there. We will be having an exam. November 4th is next Wednesday, and that is when the exam will open. It will be online on Canvas. It will be 25 multiple choice questions, all from ASA and from the ASA and Jefferson study guide, okay, on batteries. Everything that we covered on NiCad, lead acid batteries, sealed lead acid batteries, charging, everything from your ASA study guide, Jefferson study guide. It'll be a mixture of those two study guides, but both of them have almost identical questions. So, okay, November 4th. That will open, and it will be due Sunday, November 8th by midnight. So you will have that Wednesday to do that, and then all the way into the weekend, and then it will be due. We will not have lecture on Wednesday, November 4th, and you will not have a quiz on November 4th. The test will serve as your attendance. And then secondly, if you do not know already, the campus is open. So labs have resumed in person. We'll be in lab tonight. And if you are in my NavCom class, we will be in lab tomorrow. Okay, so I'm going to get started. As always, if you have any questions, go ahead and type them in the chat. So we finished batteries, and we are going to, hang on, let me plug my laptop in here, else it's going to die. Okay, so we finished batteries, and now we're going to spend the remainder of the semester on AC circuits, alternating current. So today we're going to go over a little bit of an introduction and some terminology with AC current. So beginning with alternating current and voltage, we'll go through cycle and frequency, phase relationships, values of alternating current, and opposition to the current flow of AC. Starting with alternating current and voltage. AC systems have largely replaced DC in commercial power systems. AC can be transmitted over long distances. AC voltages can be increased or decreased by use of transformers. This makes it more economical than DC. So comparing AC and DC, the advantages of AC are that it saves space and weight because AC devices in general are smaller and simpler than DC devices. Also, AC circuit breakers operate well under loads at high altitudes. Arcing is a problem in DC systems, and this causes frequent circuit breaker replacement. Most aircraft that are using a 24-volt DC system require special equipment. So that is another advantage to AC. I'm going to correct this because the word equipment is missing. So just another advantage to AC. DC does require special equipment. Differences of AC and DC. power. DC flows constantly in one direction only. It has a constant polarity. And DC changes magnitude only when the circuit is opened or closed. In AC circuits, it changes direction at regular intervals. It increases in value at a definite rate, from 0 to a maximum positive value and back to 0. And then it will deflect to a maximum negative value and back to 0. AC can also flow in the opposite direction while increasing to a maximum negative value and again decreasing back to 0. AC constantly changes direction and intensity, which causes the following effects. We have to account for the effects of inductive reactance and capacitive reactance. These effects do not occur in DC circuits. Cycle and frequency. Cycle defined. A cycle is a repetition of a pattern. The cycle is represented by the symbol of a wavy line in a circle. So I wrote this out for you because, and this is the wavy line that you'll actually see, but it will have a circle around it. I could probably draw it on here, but I don't know how. So just keep that in mind. You can Google that if you don't know what I mean, but that is the symbol meaning a cycle, representing a cycle. So here's an example. This comes out of your 8083. This has an example of a few of the definitive terms we're going to be talking about. So cycle, right here you can see in this image, one cycle is right here. And there's some steps here to describe that cycle. The voltage starts at 0. So we're talking about right here. It increases to a maximum positive value, which is up here, positive alternation. Decreases to 0, which would be met right here. And then increases to a maximum negative value. Here's our negative alternation. And then again back to 0. This is what constitutes one full cycle. So that's what this diagram is showing, our one full cycle here. It deflects to a positive peak, a negative, back to 0, a negative peak, and back to 0. And then this cycle continues multiple times. So like here we have our second cycle. There are two alternations in a complete cycle. We have the positive alternation and the negative. Each of these is half of a cycle. So going back to our image, this 0 point, this 0 point is only half of our cycle. We have our positive alternation. So both of these make up a full cycle. Sorry, my dog is barking. Simba. Hey. Okay, so cycles and frequency. Frequency defined. Frequency is the number of cycles of AC per second, per 1 second. The standard unit of frequency measurement is the hertz, Hz. We also have period, period defined. The time required for a sine wave to complete one full cycle is called the period. So we have cycle that is defined as that length where the sine wave is going from 0 to a positive maximum, back to 0 to a negative maximum, back to 0, and that's our cycle. The time that it takes a sine wave to complete that is the period. So that can be confusing, but the period has to do with time. So the period of a sine wave is inversely proportional to the frequency. The higher the frequency, the shorter the period of the sine wave. And wavelength. This is the symbol for wavelength, and it's actually the Greek letter lambda. I can figure out how to type it in here, so just so you guys have an idea. If you are looking at a wavelength, it will be identified by this symbol. So wavelength is the distance that a waveform travels during a period, is the wavelength. I think I have another, yeah, so going back to our image here, here we have one wavelength distance, okay? We have our one cycle, our one period in time, and one wavelength in distance. So keep that in mind, they all interact with each other. The distance that this waveform travels during the period is the wavelength. Identified by Greek letter lambda, the measurement is taken from one point of the waveform to a corresponding point on the next waveform. Okay, so in this wavelength, the distance is taken from point 0 to point 0. Phase relationship. Phase is the relationship between two sine waves, typically measured in angular degrees. In a circuit that is supplied by one alternator, there needs to be a phase relationship between voltage and current. In a system fed by two or more alternators, there must also be a phase relationship between the individual voltages and the individual currents. We can compare two separate circuits by comparing the phase characteristics of one to the other. These are examples of your phase conditions. So you can have a out of phase condition, depending on how that's measured in degrees, and you can have an in phase condition. This diagram comes directly from your 8083 handbook, and it's pretty useful. So in this first diagram, you can see that the voltage and current, this is then an in-phase condition, okay? We'll come back to that diagram. In that figure, and this is the figure from your book, this shows a voltage signal and a current on the same time axis. When the voltage increases in the positive alternation current, current also increases. When the voltage reaches its peak value, so does the current. Okay, so it doesn't mean that they're exactly the same, but they move the same. So both of the peaks are together. You know, the voltage has its peak, the current has its peak, and then it moves together, and same with the negative deflection. That is an in-phase condition. When two waves are exactly in step with each other, this is an in-phase condition. Two waveforms go through their maximum and minimum points at the same time and in the same direction. So this is the same diagram. But when we're talking about an out-of-phase condition, this is when two waveforms go through their maximum and minimum points at different times. A phase difference exists between them. This is an out-of-phase condition. So the other two images on the same diagram show out-of-phase conditions at different degrees. This middle diagram here, we have two voltage waves out of phase at 90 degrees. And this is what that looks like. This would be the diagram of that sine wave. If we had an out-of-phase condition of 180 degrees, it would look completely opposite of each other. Cautionary note, when two signals are not locked in phase and become mixed, damage can occur to the aircraft systems or avionics. Values of alternating current. We have instantaneous value, the induced voltage or current flowing at any instant during a cycle. This literally is any point on the sine wave could be considered the instantaneous value of voltage. So the value at any instant is pretty much what instantaneous value means. The peak value. The peak value is the largest instantaneous value, largest. The largest single positive value is at 90 degrees. The largest single negative value is at 270 degrees. Maximum value is 1.41 times the effective value, and we'll talk about effective value next. These are called peak values. Effective value. This is also known as RMS value, which means root mean square value, and that just refers to the mathematical process of how this value is derived. Most aircraft voltmeters display the effective or RMS value when used. The effective value is less than the maximum value, so 0.707 times the maximum value. So effective value is actually 0.707% of the maximum value. In math terms, you would take the maximum value and multiply that by 0.707, which is about 70%. That's your effective value. Effective value is a measure of the heating effect of the sine wave. Alternating current voltmeters and ammeters measure effective value. So alternating AC measuring instruments, the readings that they provide are in the effective value. And in regards to AC circuits, any values given for current or voltage are assumed to be effective values unless otherwise specified. So any values you're reading are always effective values unless specifically notated otherwise. In practice, meaning in real-world application, effective values of voltage and current are used. AC measuring instruments, once again, voltmeters and ammeters, measure an effective value. Effective voltage of a sine wave, of an AC sine wave, is 0.707 times its peak voltage. The effective voltage is the voltage measured by most of the AC voltmeters, and peak voltage is measured with either a special peak voltmeter or an oscilloscope. So reading actual peak voltage, you need a special reading instrument. And power factor. There is a power factor in AC values. There we have apparent power, which is the circuit voltage multiplied by all the current. We have true power, which is always less than the apparent power in a reactive circuit, which is any AC circuit containing either inductance or capacitance. So any reactive circuit is an AC circuit containing either inductance or capacitance. And we have a formula for our power over our apparent power. So you might see in your study guide or on your test a question like, calculate the power factor given true power is a certain coefficient and apparent power is a certain value. Okay, so you will need to know that formula. It's not something that's largely talked about. This is just something that is mentioned for general electricity, so just know that that formula is there. It's not complicated. If you need to figure out the power factor, it's true power divided by apparent power, and those will always be supplied to you or will be, annotated on a drawing, so they're not hard to find. Opposition to the current flow of alternating current. We have three factors that influence current flow on AC circuits, and they are resistance, inductive reactance, and capacitive reactance. Resistance, measured in ohms, has a direct influence on AC regardless of frequency. Inductive reactance and capacitive reactance oppose current flow only in AC circuits, not in DC circuits. Note, capacitors may also create an opposition to current flow in AC circuits. So the three factors that we are talking about here are the three factors that most influence, but just know that capacitors have the potential to create opposition to the current flow as well. And inductive reactance and capacitive reactance can potentially create a phase shift between the voltage and current in AC circuits. So not only can they affect the current flow, but they do have the potential to affect the phase. Whenever analyzing an AC circuit, it is very important to consider the resistance, inductive reactance, and the capacitive reactance. All three factors influence the current of the circuit. And that's it. That's all the slides for today. Going over a little bit of an introduction for AC circuits, alternating current. We will, in next lecture and the following lectures, be getting further into impedance, inductive reactance, stuff like that, more detailed into these things that affect AC current, okay? So that's all for the slides. The slides will be loaded on Canvas tomorrow. Lab is on today. It is live on campus. You do have a quiz that will be due today, so review the lecture as needed. That is it for today. If you don't have any questions, then I will see you on Monday for lecture. If you do have any questions, please type them in the chat. And don't forget that we have an exam coming up. I will remind you guys, I also posted it on Canvas. I posted an announcement, okay? Okay, looks like everybody's gone.